Dear colleagues, there is one item in our agenda today, the public defense of doctoral series, Mr. Pejman-Rasti, analysis of remote sensing, image super resolution using fluid lenses. According to our regulation, in order to proceed, we need presence at least 6 members of council. This we have, including also additional members, Professor Vitali Skacek through Skype, thank you, and Professor Olav Mertens from Tallinn Technical University. So, I declare the meeting open. Ladies and gentlemen, first of all, I would like to welcome Professor Dr. Enis Cetin through Skype from Department of Electrical and Electronic Engineering, Bilkent University, who kindly agreed to act as official opponent of this defense and is taking part through Skype connection. So, from San Diego, as I understood. Let me remind in brief our schedule. In the beginning, the word is given to our secretary to introduce the defendant and the documents he presented to council. Then the floor is given to the defendant for 25 minutes for presenting the main results of the thesis. It will be possible after the report to ask short questions concerning the report. However, the main discussion will take place later. After the report, there follows academic disputation with official opponent. And then general disputation is opened, where everyone can ask questions and or express his opinion on dissertation. After the disputation, the word is given to scientific supervisors for characterization of defendant and his research. After the discussion, the defendant will have his final word. Then the meeting continues with closed session, where the decision on awarding the degree will be made by council by secret balloting. It will be announced, the results, as soon as May. So, now I ask secretary to introduce the defendant. Dr. Arjanen, please.
Thank you. Dear colleagues, this defendant, Pejman-Rasti, has made his Bachelor of Science degree in Azad University and Master of Science degree in Eastern Mediterranean University. After that, he has continued his studies in the University of Tartu and is now then making his PhD degree, the final examination. As I see from the papers, he has experience in different laboratories, also including companies. He has also professional duties, a list of papers where he has been reviewer. But the main point is also that he has got all credit points from our university, which are needed for PhD defense. All together there are 179 credit points, from which 119 is for the PhD work, and then other studies is 60. And he's allowed to defend thesis today. Thank you.
Thank you. Any questions? Not the case. Then, Mr. Rasti, the floor is yours for 25 minutes for report the main results.
Thank you. Excuse me. Do you hear me properly through the Skype? Yeah. Okay. So Good morning. Thank you very much for coming to my PhD defense. My name is Pejman, and the title of my thesis is Analysis of Remote Sensing Image Super Resolution by using Fluid Lens. My supervisors are Associate Professor Ghulam Reza Anbar Jafari, or Shahab, that's here, and another my supervisor is Professor Rodolphe Kiefer. He's not available in this session. So, at the beginning, I will talk about the problem that we are facing in this thesis. After that, I will describe the proposed liquid lens that we had, and then I will start talk about the super resolution algorithms that we proposed, and at the end we will see application of super resolution in other areas. So, my thesis consists of two parts. The first part is about the liquid lens, and the second part is about the image super resolution. The problem that we have for the solid lens is that in a small cameras, we don't have enough room in order to move the solid lens or rigid lens through the focal length. For this problem, we can propose a liquid lens, and for the liquid lens, we don't need space. We just have to apply voltage to change the focal length. So, the basic concept of the liquid lens is like this. We use two liquids, one in top, one in bottom, and a membrane with a central hole in between these two liquids. For all proposed liquid lens, we use the silicone oil at the top, the first liquid, and just the still water as a second liquid, with a membrane, as I said, with the central hole. If we use a membrane with the contraction property, easily we can change this curve, because when we use two liquids, we can make this meniscus shape or the curve. If we apply voltage to the membrane with the contraction property, we can change the meniscus shape or the curve, so it changes the focal length if we pass the light from this. So, as I said, the most important part of this lens is the membrane. We use dielectric elastomer actuator, but not just a layer. We use a stack of dielectric elastomer actuator. The membrane is a fabricated automatic system. First, two components of PDMS is mixed on the spin coater disc with a specific speed. This speed defines the thickness of the layer that we want. And then we use temperature heating here to speed up the process of fabrication. And then the graphic powder sprayed on the layer, of course that with a shadow mask, to have the electrode on the layer. This process repeats based on the layer that we are required for making the dielectric stack actuator. So, if we apply voltage on the membrane, not in the pressure of liquids, the normal situation, we can see that if we increase the voltage, for example, to around 2.1 kilovolt, we can have around 5% contraction with the membrane. But we made two membranes. One has the active area of 40 millimeters, and another has the active area of 20 millimeter. And for the membrane with the active area of 40 millimeter, we have around 5%, and with the 20 millimeter, we have around 4.3% contraction at the central hole. So, this is a schematic of our lens. We use the oil at the top and the water at the bottom of the membrane, and this is the membrane with the active area of 40 millimeters. For testing the lens, we pass a light, actually it's the laser beam, through the lens and measure the size of the light on a plate here. With this configuration, the distance between the lens and the laser is 200 millimeters, and between the lens and the plate is 440 millimeters. So if we measure the size of the light on the plate, we can see that at the beginning that we haven't applied the voltage. It's the size is around 6 millimeters on the plate. But when we apply the voltage to, for example, 800 volt, we can see that the size of the lights on the paper will change, or we can say that the focal length will increase because the size will, the local length decrease because the size is increased. So if we compare or purpose liquid lens with some of available liquid lenses, let's share, for example, these three, we can see that we significantly drop the driving voltage from, for example, the minimum between these three is 1.8, but for our work it's around 750 volt that we required for the lens. But here also we can see that for the electrode they use the carbon grease, the graphic powder, and also we use the graphic powders. So, and from this we can see that we have the same focal length, but with less driving voltage. So, the second part, that is image super resolution. Actually, in general, I can say that we use the super resolution because, as I said, in the small cameras, we don't have that much place to use a big sensor with lots of pixels. And also, if we have the place for that sensor, the sensor has the cost for our work. So instead of that, we can use image super resolution algorithms. What it do is that the super resolution algorithm generate a high resolution images from one or a multiple images, low resolution images. So at the beginning, we use a method for enhancement the resolution of the satellite images. As you know, we can use just image interpolation in order to enhance the image. But when we use the normal interpolation by the kernel-based normal interpolation, at the end we have a smooth image due to interpolation. It means that we don't have that much sharp image. To have more high frequency that causes to have a sharp image, at the beginning, here we use a pre-processing for denoising an image with a well-known denoising image. After denoising, instead of applying the interpolation on the low-resolution images, we apply the discrete wavelet transform in order to decompose the low-resolution image into 4 subbands. One is low resolution, one is low frequency details, and other 3 have high frequency details in vertical, horizontal, and diagonal direction. So, if we apply the interpolation we can use the normal interpolation bicubic. We can just on the high frequency detail and in parallel on the low resolution image, and at the end, if we use the inverse discrete wavelet transform to combine all these subbands, we can generate a sharper image or an image with more high frequency details. So If we compare it with other algorithms or other filters for denoising, we can see that the PSNR results that is presented in the decibel dB is more than other algorithms that we have here. It's 30.82. And here you can see the visual, it's the low resolution, noisy images. After the applying the super resolution algorithms, or after doing the enhancement on this, we can find this one. Also, it's just 3 rows of the table. You can see the detailed table with, and the comparison with other algorithms in page 64 of my thesis. So, as I said, if we use interpolation, normal interpolation, we will have a smooth image. So, one of the solutions to solve this problem is using some kernels that return more high frequency and more benefits for us. So, in this work, I proposed 2 kernels, Sing exponential and the Lanczos kernel, and we combine these 2 kernels with the alpha blending algorithm in order to generate a high resolution image from a low resolution image. So, as I said, we use these 2 kernels. The reason that why we use this kernel is that for the Lanczos kernel, from its property, we know that it's good, it's worked well for the smooth areas of the image, but due to Gibbs phenomenon effects, it's not good for the counterpart or the edges, the parts with the edges. So we can use it for the smoothing part, and another kernel that we propose is a Sing exponential. That this kernel works well for the contours or edges, but actually it's not that much good compared with the Lanczos for the smooth area because it's a little sensitive to noise. So if we combine these 2 kernels, we can benefit of its properties for the Lanczos from the smooth area and Sing exponential for the contours parts. So we combine these 2 kernels with an alpha blending algorithm like this, but for defining the value of alpha, we did some tests. So here we used the different value of alpha here for around 1,000 facial image and around 1,000 non-facial image. And from that experience, we found that the alpha values will be the optimal alpha value for the facial images is around 0.8. But when we are working with the non-facial images, we can choose the value of alpha as a 0.6. And we just combine these 2. It's with the alpha blending, it's the alpha, the generated image by using the Lanczos kernel, and this is the generated image by using the Sing exponential. So, to test these 2 kernels, we use with the combination with the alpha blending combination. We use the 2 well-known super resolution algorithms. One is sparse representation super resolution, and another is example-based super resolution. And we use these 2 kernels as an initial interpolation of these algorithms. It means that we adopt these algorithms, and we just change the kernels for the initial interpolation. So, and we tested it on the average of 2,000 images. We see that if we use the BSP line kernel as a kernel of the initial interpolation, we will see that the PSNR 25.29, 25.88, But if you use the bicubic kernel, that is the default kernel that they use for their works. For the SPARS representation is 27.39, it's in the decimal, it's the PSNR results. And for the example-based super resolution is 26.10. But if we use purpose kernel or suggested kernel, Lanczos and the Singh exponential, we can get the PSNR of 28.64 or 27.84 for the example-based. So we see that these two kernels perform better for the super resolution algorithms. Also, you can see the detailed tables in page 74 to 77. We use other quality measurement criteria. I just showed the PSNR results, but for example, SSIM, that's the structural similarity on the paper, on these tables, and also you can see the other images and the visual results of these works. And the last algorithm that we proposed, it's a novel low complexity algorithm for the super resolution. For this work, at the beginning we have to make a high resolution dictionary and the low resolution dictionary of the patches. So it will be a huge dictionary that consists of lots of patches. For example, here for making the high resolution dictionary, we used around 600 images from different categories: face, remote sensing, non-face images, and other categories. And we extract the patches of the images and saved in the high resolution dictionary. And on the other hand, we use the low resolution version of them in the low resolution dictionary. So we make this dictionary once and we use it several times for super resolution. So if we use a low resolution image as an input, at the beginning we extract patches from the low resolution images, and we find the distance of these patches that are extracted from the low resolution image with the available low resolution patches in the dictionary. And then we will select the patches in the low resolution dictionary that has the minimum distance with the extracted patches from the low resolution dictionary. And with the map function between these two dictionaries, we can extract the high resolution patches from the high resolution dictionary, and for each patch, we have a corresponding high resolution patch here. If we just put these patches, the extracted patches, next to each other, as these patches are extracted from different images, we will see a blocking effect on the image. So it's not a good idea to put it next to each other to make the super resolved image. So to solve this problem, we suggest a mean shift algorithm. What we are doing in the mean shift, we shift the mean of each patch, high resolution patch, to be the same as low resolution extracted patches that from the low resolution image. So if we do this mean shifting, here we can use these patches in order to make the output. And then if we combine it with the initial interpolation that we have here, as I said, we can use the different kernels, bicubic or proposed kernels for the initial interpolation, and we generate the high resolution images. So we tested our algorithm with the two state-of-the-art algorithms, the sparse representation super resolution and the super resolution by using convolutional neural network. In different categories, for example, we use the agricultural, that consists of 100 image, airplane images that consists of 100 images, and the facial images, it's 1,000 images. We can see that the PSNR results of our works more than the PSNR results of the other works. And also we compare our algorithms with the other state-of-the-art algorithms. You can see them on page 78 to 81, and also we use other quality measurement criteria for our comparison. So, as a visual result, you can see, for example, for one of the super resolution algorithms that we used, another one, and the sparse representation. For the visual one, if we cut these parts from this area of the zebra, we can see that also we have the better visual results compared with the other algorithms. Also, you can see more images in page 78 to 80 for this comparison, visual comparison. As I said, we have a huge size of the dictionary. So the problem that we have in this dictionary is that as we are extracting paths from lots of images, there are some patches that are similar to each other or close to each other. In order to reduce the size of the dictionary, we propose the two approaches. One is find the Euclidean distance between the vector of the singular value of each patches, or find the structural similarity index of each patches, and if it's less than threshold, we can remove it. If it's more than threshold, we can keep it. So, by these two approaches, we can see that we can decrease the size of the dictionary by around 70%. Why? We just lose, for example, if we use the SSIM, structural similarity algorithm, we lose just around the 0.3 dB of the PSNR, but if we use the SVD, we will lose around 0.5 dB. And it shows that instead of using the huge dictionary, we can reduce it and use it, because if we use the small size of dictionary, our system performs faster for our work. So at the end, we use super resolution algorithms in other areas, such as face recognition in surveillance monitoring, the work that's published in the AMDO conference. We also use the super resolution to improve the action recognition, the work that is published in IPTA conference. And the last one is using the super resolution to improve the recognition of pain, that is published in ICPR last year, 2016. So, at the end, I would like to say that in the period of my PhD, I had a good collaboration with a well-known university, University of Darmstadt, Technical University of Darmstadt in Germany, that helped me a lot for the fabrication of the lens. And we had a collaboration with University of Barcelona, University of Aalborg in Denmark, and Tallinn Technical University in Estonia for the super resolution parts of my thesis. And from this collaboration, more than 20 papers have been published on the top ranked venues. That here we can see a list of published papers of mine, and that's it. Thank you so much. You should thank them.
Thank you. Is there any short question that needs immediate answer now? Not the case?
Yeah.
Yes, I have emailed these questions to Pejman.
Yeah.
And
But I will give with you immediately. So you can. The next, I ask you, Professor Chetin, to give us your opinion on the dissertation, recommendation, and if there is any criticism or question, the defendant responds immediately, and so there will be a kind of dialogue between you. So I will give words to you, Professor Chen.
Thank you very much. So we can go over the questions one by one.
Okay. Yeah. Okay. So, as the professor sent me the questions, let me.
Okay.
Yeah.
So, just a second. Okay. So, my first question is, what's special about the Blackman-Harris kernel? Can you use Kaiser window or Henning or Hamming windows?
Yeah. Actually, we use the Blackman-Harris as a initial as a kernel of the initial interpolation in the algorithms. We know that from the properties of the Blackman-Harris, it's work well on the counterpart compared with the Lanczos. But it doesn't show a good behavior on compared with the sinc exponential. But on the other hand, for the smooth area, it works better compared with the sinc exponential, but it's not that much. It's not as good as Lanczos for the smooth area. We tried the Blackman-Harris, but it didn't give us better results compared with the proposed algorithms, proposed kernels, and it was the reason that why we just describe it and we say that we use this, but it's not in the case of using for this work. So, and for the comparison with the other kernels, so of course that we can use the other kernels for the works, but as I know, the Kaiser windows acts like the Blackman-Harris kernel, and we expect to see the same results compared with the Blackman-Harris by using these windows. And for the Hamming or Hanning, that is which is referred to a hand kernel or hand function, we can say that we tried these kernels, but the results was not comparable with the proposed algorithms. But yes, we can use other kernels. We have to modify the parameters and use it in the special cases that we want. But maybe for other purposes, the other kernels will work well. But for our work, that is that's the purpose kernel for the initial interpolation in the super resolution. These two kernels, Lanczos and the sinc exponential with the alpha blending algorithms, show a good result for us. So.
Okay. So the second question is wavelet-based interpolation equivalent to kernel-based interpolation?
Yeah.
For example, you can use Haar wavelet for one interpolation scheme, and then you can use the smooth wavelet like Dobeshi, long-order Dobeshi filter, again for interpolation, and then you can alpha blend these two.
Yeah. Yes, you are right. at the beginning, let me to answer the first one. That's the difference between the normal interpolation or the kernel-based interpolation with the wavelet. As you said, and you mentioned it, and I said, if we use the kernel-based interpolation, or we can call it the normal-based interpolation, we will see a smooth image at the end. But when we applied the discrete wavelet transform on the low-resolution image, and then we apply the interpolation on each subband, we know that from the isolated high-frequency details, if we apply the interpolation on the isolated high-frequency components, we will see more high frequency as a result. But for the other wavelet function that you mentioned, yes, we can use the Haar wavelet and or other function, wavelet function for our work. But here we use the function of DB9/7 for our work. That is that represent the lowest, the smoothest frequency for our work. But yes, for other function, we can use the other function of the wavelet for decomposition, because all function of the wavelet returns the high frequency in the three subbands in the different directions, and we applied on them. It's not that much. I cannot say that much important, but we can use other kernels for as a wavelet.
Okay, but you can also try interpolating images without decomposing it. Whatever you have, you use it as whatever image that you have, you use it as the low image, and then you interpolate it using the Haar filter or some other wavelet. You may try this later. Okay.
Yeah.
Did you understand what I'm saying?
Yeah, I got your point. As for the low frequency subbands, also we can use this
subband. I mean, not decompose it. You just use the synthesis part of the filter.
Yeah, sure. Sure. So,
okay. Third question. Why did you use the L2 norm in equation 3.23? This refers to the thesis. The number refers to the thesis in the regularization term.
Yeah.
Can you use the L1 norm? Because nowadays the L1 norm is more popular compared to the L2 norm. And what's the advantage of L2 norm over the L1 norm?
Yeah. At the beginning, I should mention that the equation 3.23 is related with the adopted super resolution algorithms, example-based super resolution algorithms in our work. We didn't change the parameters of the algorithms because we wanted to see the reaction of the algorithms for the kernels in kernels. But in general, the author of the papers for the example-based super resolution tried also the first norm 1, L1, in their work, but not in the last one. In the previous one, they used the same algorithms, but used the first norm. And for the next works that is reported here, they use the norm 2, and their motivation is that the norm 2 is differentiable for their works, and it was their motivation that they used in the algorithms. But in general, as you know, yes, these days Norm 1 is popular because of its sparsities, and it will represent the multiple solutions. But as we know, for the Norm 2, we can have the uniqueness solution. It represents the unique shortest path for the work, and also it's differentiable for another property, and it has the computational efficiency. It is the advantage of the Norm 2, but apart from these properties, when we are using the regularization term for our work, it's highly dependent to the first parts of the function, that sometimes it shows a better performance with using the Norm 2, sometimes it shows the better performance with the Norm 1, but we know that for the Norm 1 we have to find the absolute value. We cannot, it's not differentiable, and as I said, their motivation are using the Norm 2 is the property of differentiable for their work. But also, as I said, they reported the results for the same algorithms in the paper that is published 2 years before that, by using the Norm 1 as a regularization term.
Okay,
Yeah.
so my next question is, how do you determine the blending parameter alpha?
Yeah.
Now, you have, of course, this slide in your presentation.
Yeah.
I guess it is you are just displaying there.
Yeah.
My question was that how did you obtain this? And I guess you obtained by experimentation.
Yeah, we find the optimal value with the experimentation. As I said, we use the different value of the alpha. Here, for the facial images, 1,000 facial images, that I think it's enough for the experimentation, and also non-facial images from different categories. And by this experimentation, we define the value of the alpha as 0.6, around 0.6 for the non-facial, and 0.8 for the facial images. Yeah.
Okay. And the last question, have you tried this generative adversarial networks, GAN, for
Yeah.
super resolution instead of ordinary neural networks?
Yeah. So actually, the algorithms that Professor mentioned is the recently published. It's very new and it's very hot in the term of super resolution. It's published. It's published in around 1 month ago, and they use the GAN for the loss function. So, but yes, it's very well algorithms that also can help in this area. But as you know, the super resolution algorithms based on the deep learning structure are very popular these days because it shows a good performance for the results for the images, but it has the place for improvement when we are working on the loss function of them. So they suggest GAN to solve to get the better results, but as they also mentioned in the paper, the GAN works well on the higher scales, 4, 8, or more than this, and especially from the visually, as they mentioned in their papers, visually it shows better visual results compared with the state-of-the-art algorithms. Yes, this is the perfect algorithm. I work with some algorithms in the deep learning. such as super resolution by convolutional neural network for very deep convolutional neural network. But yeah, I haven't worked with this. But when you wrote me this, I found the paper and I start to read it, and with high probability, 100%, I will work on this in the future because it's very well algorithms in this area.
Okay. So these were my questions, and the candidate answered them properly.
Yeah, thank you.
Professor Çetin, I want you to give us your opinion about the level of this PhD work and about question giving him academic degree.
I found the thesis acceptable, and the candidate is well prepared. He is fully competent on the material that he presented in his thesis, and he answered my questions in a proper manner.
Okay. Thank you, Professor Çetin. And finally, I want from you a written opinion or review about this thesis, signing you and send this to the university. Thank you.
When should I send this written report?
As soon as possible.
Can I do it this afternoon?
Yeah, it's possible.
Because I need to get university letterhead.
Yeah, thank you.
Okay, thank you very much.
And now the thesis is open for general discussions. So, please. Yeah.
If I can ask, maybe the first question is about your motivation. What was the most motivating to start with just this topic? And also, maybe what was the most interesting part or most challenging? And maybe also from the application viewpoint, what could be the most interesting for you and most?
The first motivation on the liquid lens part is that, as I said, for the small cameras, as these days the cameras will be smaller and smaller. We have to find a solution if we want to see the range of the focal length. So one of the solution is using the liquid lens for this. It's the main motivation that I work on this. But as I said, as you mentioned it, the challenging part of this work is that we have lots of limitation for the fabrication of the liquid lens, for using it on the other areas, because at the most important part of that, using the high voltage for the driving, the driving voltage. For example, here, as I said, just a second, said we need 750 volt for the driving voltage of the dielectric arsenal actuator, but it has the place for improvement on the liquid lens. For the second part, that's the super resolution. As I said, the first motivation is to reduce the cost of the system. If we use a sensor, for example, in our work, after 1 or maybe 2 years, we have to buy a new if we want to improve our system, and it make a cost for our work. But if we use the image super resolution, without any cost, we can find a high resolution image. And on the other hand, if we, for example, if we are working on the satellite images, if the the images that are taken from the satellites wants to send to the center by the original size, it needs a lot of bandwidth, a big bandwidth, but they reduce the size and we reconstruct it on the center. It was the most important part, and the more challenging parts in this work is that for the single image super resolution, we need a period because we just have one single image and we have to generate the high resolution from that single image. And the most important is the period that we want to find. And at the end, we estimate some values. If we cannot use a good period, we cannot estimate a good value for the new pixels that we used for the super resolved image.
Okay.
Yeah?
Okay. And then around your title, it is about remote sensing image.
Yes.
And remote for me means from satellite.
Yes.
Or is it 1 meter also?
Yeah.
In this your context?
Yeah.
Remote 1 meter.
Yeah.
Is it satellite?
No, it's the satellite images. We use for the satellite images, and we on the thesis also we shows that for the other image categories, such as for example facial, non-facial, and other, or algorithms are that enough robust to do that and that.
My question about this part is that you have some images from the satellite,
yeah.
but not so many. Mostly this Lena with the head and so on, faces and so on and so on.
Yeah.
And but still there's a title. I
Yeah.
have the feeling that you have everything about this Lena is also from the
Yeah.
satellite.
But
so on. But the question is
yeah.
how this from the satellite are the images somehow specific compared with this, for example, Lena and so on.
Yeah.
Faces and
Yeah.
so on. Are they anyhow specific?
Yeah.
Any specific?
Yeah.
Different approaches compared with.
Yeah. So. Yeah. Actually, for the satellite images, we use around exactly 21 categories of the remote sensing images. For example, you can see the categories at the page 78. That each category consists of 100 images, and it means that 2,100 images for the satellites, and we showed that the algorithms work well in this area, especially when we are using the discrete wavelet transform for the satellite images, because you know when we take an image from the satellite, details are important for us, because for example when we take an image from the Earth, we want to see the ocean, or for example in the closest countries. It means that we need more high frequency details in the image in order to show the more details. So if we use the algorithms that give us high frequency details, we can use it on the remote sensing. But for the facial images, as we are just working on the face, maybe the most high frequency details on the hairs, and it means that if we can use the algorithms that works well on the smooth area, for example for the face, but for the remote sensing we have to use some algorithms that works well on the high frequency details of that. Yeah.
Excuse me, Mr. Stay or should I leave?
Excuse me, hocam. Just a second.
Yeah.
Yeah. Could you please repeat?
Should I stay or should I leave? I don't know the rules.
They know the rules.
Usually, opponent is taking part also from this.
Open. Okay.
Yeah.
Yeah.
Even for he cannot vote, but he can hear discussion of members. So if you can be there, so.
Yeah.
That's good. So, any other questions?
Yeah.
For obtaining the high resolution image, first thing one should have is high quality optics.
Yeah.
And this means in particular one should have as small aberrations as possible. So
Yeah.
have you estimated or could you say about the aberrations of liquid lenses which you used or in general as compared to solid lenses?
Yeah. Of course that if we use the solid lens, we can get a better or the higher resolution images compared with the liquid lenses. But the most important parts for taking the high resolution image is the CCD sensor that we used behind the lens for to take the image. Because if you use the big CCD sensor with the high pixels, we can get the more high resolution images. So if we use the big sensor and also the different lenses in order to take the image, as I said, we have to pay a lot for this. It means that it increases the cost of our work or system. But we can suggest a solution that the solution is the super resolution, that if we use liquid lenses or the small sensors for the optic sites, by the super resolution algorithms, we can generate a high resolution or estimate the high resolution image that is actually close to the actual high resolution if we use the big sensor and some solid lenses. So if I got your point and answered it correct.
Thank you. Professor Skacek, want you also ask some question?
Yeah. Can you hear me well?
Yes, yes.
So one thing that I was puzzled about, I was interested in your interpolation of a kernel that you're using, which works better than the other kernels or interpolation that you refer to. Why it works better? What is the intuition? Why? Or how do you? Yeah. What is the intuition behind why it works better than the other?
Yeah. As can I describe it over the slides? Yeah.
Yeah. Absolutely.
So, as I said, when we use the Lanczos image, Lanczos kernel for the interpolation, compared with the bicubic or other kernels, we can have a good estimation on the smooth area. It works well on the smooth area Lanczos. For Lanczos kernel, it works well on the smooth area, and it's the reason that why we chose this one as one of the kernels. But as you know, the kernel it has the Gibbs phenomenon or Gibbs effect, or in other words, ringing effect. Because of this, suddenly drop to the negative. So it's the reason that why it's not that much good compared with the other kernels for the counter or the edge parts. So on the other hand, if we use the Singh exponential, we can benefit of its property on the counters. But as I said, as you know, from the properties of the kernel, it doesn't work well on the smooth area compared with the Lanczos, because from the properties it's sensitive to noise, and it involves some noises on the images. But if we combine these kernels, we can benefit of both advantage of them. So if you combine these two by alpha blending, or we suggest alpha blending, but we can use other combination algorithms, but I think the alpha blending is the best one. We can get benefits of the goodness of the lines in the smooth area and the goodness of the sinc exponential kernel on the counter area, and at the end we can see the better in the interpolated image compared with, for example, the common, that is the bicubic or nearest neighbor or the bilinear kernels. That was the motivation to use these two kernels, or to propose these two kernels for the initial interpolation.
Okay, I see. And I have a general comment. I have just general comment.
Okay.
I understand that probably this is the way how it's done in your area, but to me, like, things were very kind of on a high level. I understand that those are known algorithms, but I would like to see more, the semantics and going more into specific details of how these interpolations are done and so on and so on. But that's just a general remark about the presentation.
Thank you.
I ask also a question.
Please.
Can you show us a comparison with lenses you have?
Here. Yeah.
Okay. Nowadays, in Europe, lenses, there is a tendency that people are using bigger lenses.
Yes.
So you did opposite. You showed that is possible to use smaller lens. What is the main thing you did that you can to do this diameter? What's the main
reason?
reason?
Actually, because of that lacking a space on the small camera, if we want to make a big central hole or the big lens space, we need more place in order to generate a bigger elastomer actuator, dielectric elastomer actuator with the bigger active area. So from the literature, the biggest size of the lenses or to shape is 8 millimeters. That we can by that we can get 15 centimeter to 15 to 50 centimeters of the focal length by the driving voltage of the 1.8. But we can achieve the same, almost the same focal length, a little less than this, 6 and 5 in the minimum and maximum, but by this, the size of the central hole. So, if we want to take the bigger size of this, we have to make the elastomer or the membrane bigger with the bigger active areas to get that focal length. So we also tried different membrane, for example this one and this one. Also we tried several membrane with the different central hole, and it's I can show these to you. Sorry. I used several with the different central hole with the different active areas, like this, but as a result, we got almost the same result of the focal length, the same driving voltage for all of them. So it was the reason that why we chose the 4 millimeters as the size of the central hole here. Yeah.
Any other question?
Yeah.
My question is about the stability in time of these lenses. Can you explain, and are there some temperature effects because we are having liquids, they are expanding or contracting, whatever?
Yeah. Thank you for your very good question. as I said, we have lots of limitation for using these lenses. For example, as we are using the liquids, we cannot use it on the satellite because the temperature is very high. It's frozen at that area. Or if we use, for example, under the electromagnetic field, when we apply the electromagnetic field, maybe because we are using the liquid, we have the reactivation for the lights in the liquids. But it is the limitation of the liquids, not just all purposes, but in general, this is the limitation of the liquid lens that we have to work on this in order to suggest the better, to find the liquids that pass through these limitations. But as I said, it has some limitation of using, for example, the high temperature, in the very low temperatures, and for example, when we apply the electromagnetic field. Yeah.
More question?
Yeah.
The math is pretty general. The math is pretty general. As a person who has to make these lenses, is there any restrictions? What I have to consider that you can use the math later?
You mean?
Is there any limitations, physical limitations?
Yeah.
How big they can be, how small they can be, distance between them?
Yeah. Yeah. The first limitation for the lens that we have to consider is to the membrane that we use. For example, when we are using the PDMS, we have to, or the thickness, we have to know the breaking point of the membranes. For example, we should know that if we apply, for example, the voltage more than 2 kilovolts or 3 kilovolts, it will be broken, and it doesn't show anything for us that we can, for example, like this. For example, if we apply the voltage for example, more than 3,000 volts for this, it will broken. It doesn't work. And with we can estimate the resistance of the membrane by some equation, find a mathematical equation.
I asked about math. I know the material limitations, but what is the math limitation? If I make a lens, is there something I have to consider and I can apply your mathematical machine later? So you can, I give you lens, you can use the same logic as you have an algorithm. Is there any algorithm-based limitations?
Not that much. We just have for the whole lens, we just have to know the distance of the lights with the lens and the sensors that we have to put behind the lens to taking the image. For the mathematically, we can just find the focal length of this for the place of that. But apart from that, no. Actually, we.
The difference between the lenses, let's say 1 millimeter or 10 centimeters. You can use the same math.
Yeah, as I.
Okay. More question? I have one.
Okay.
About this super revolution.
Yeah.
Math cannot generate new information. You can use only this information you have in your low resolution image. What is limit must be in this low resolution? You cannot make this image with 2 or 4 pixels. Can you say something about these limitations?
Yeah. Actually, as you said, we cannot find the exact pixel value if we do the increasing in the resolution. But the most important parts of the super resolution algorithms is to estimate correctly the pixel intensity or the pixel value that will be close to the actual pixel values if we consider that we have the ground truth. If we downsample the image by factor of 4 or 8 or 2, this is the factors that we are using. I have never seen any papers in this area to estimate the upsampling more than 8, for example, 10 or 16. It's usually less than that. But the main important parts of the algorithms, the super resolution, is to estimate that pixel. But at the end, we have the estimation. We don't have the actual value. But if we are working just in the one low resolution, because as I said, we have two types of the super resolution images. One, you just use the one image as an input, and another type of algorithm use the multiple. If we just have one input, we should prepare a very well prior knowledge for our system to estimate the new pixels. For example, if we upsampling by factor 4, by upsampling by factor 8, if we increase the upsampling factor, of course that our estimation or the accuracy of estimation will decrease when we go for the upper higher scaling factors. Yeah.
Maybe I can expand the question.
Yeah.
Very good question.
Yeah.
Very philosophical, and I have been also surprised myself that it is sometimes possible to upsample the reality to see the better. In some cases, not all, and so on.
Yeah.
But the question is, as you know from the very basic signal stochastic theory, all this Nyquist-Shannon and so on, if the signal is band-limited,
Yeah.
the spectrum, where the Nyquist dictator of the sampling frequency, in this case we have pixels, of course. But if the signal is the image is band-limited,
Yeah.
we can always reconstruct, ideally taking infinite number of samples by this will exist, sync and so on, function scalars and so on. But if it is not band-limited, the signal, then it's impossible.
Yeah.
But
It's
some people still believe, like some signal processing,
Yeah.
random
Yeah,
people,
yeah.
Ferreira and Wesley and so on, that they can still manage with non-band-limited or whatever spectrum. But in your case, your image is practically, can you have any explanation? Are they more band-limited or more vice versa?
Yeah, but of course that a bit, as you mentioned that most of the people that works in the image processing are working in the band limited. So, and I haven't worked on the other areas for estimating the pixel values or the signals, but as you said, it's not always we cannot always find the accurate value or the exact value of the new pixels if you consider the original high resolution image. If you consider this one, we cannot find the exact value of that. It's the limitation that we cannot do that in our case. Yeah.
Okay. Any other question or opinion? Not the case. So now the word is given to scientific supervisor, Professor Gholam Reza Anbar-Jafari.
Shahov.
If I am correct. So, please.
Thank you very much. It's an honor to actually supervise Peshman. He's a very, very talented and young scientist, so I can see his future to be very bright. He was very hardworking. I think the amount of publication that he had in the last 3 years of his PhD is reflecting the amount of work that he has put and the amount of effort that he has put. He has been also a very social person. and I think he has been between so many of the labs internationally and nationally. He has put the amount of work on the thesis day and night, especially on writing part of the thesis. Lots of corrections from all who came in the Estonian language part especially. So we learned a lot in there. So I'm very honored to supervise him, and I think that it's a very, very good high quality work. Thank you, Peshman. Thank you, everybody.
Thank you.
Thank you. And now your final word.
Okay. So, as a final words, I would like to thank my opponent, Enes Hoca, and they invited internal opponent, Professor Skacic, for their attendance. Also, the jury members to take time and come to my defense. And I also would like to thank my supervisor. He said the nice words about me, but I always follow him. He helped me. He was behind me always in the work. Thank you, Shab. And also I would like to thank my wife, Salma. She supported me in all the moments of my academic study. And also today is my father's birthday. I said that from the distance I can say that happy birthday to you, and I thank my families. They are in my heart. Thank you so much.
And now our meeting is continued with closed session, so all guests, please
Should we
leave.
go? Oh.
You may stay, but not vote. Okay. Ladies and gentlemen, let me announce the results of secret balloting. For awarding the degree, 8 votes against nil, abstained nil. Basing on these results, I declare the following. On the behalf of University of Tartu, our council awarded you Dr. Benjamin Rusty, the doctoral degree, Doctor of Philosophy in Material Science. I congratulate you with awarding this degree and wish you all success in your future activity.
Thank you so much.
The official session is closed. Thank you.
Thank you so much. Thank you so much. Thank you so much.
Hocam Vitali, thank you very much. Yeah. I think the session is not closed. Thank you for attending.
Hocam, thank you.
Thanks.
Thank you so much.
Congratulations once again.
Thank you so much.